It's time. Okay, any questions from the homework or regarding the exam? Nick?
Can you go over number 1 from quiz 6, please?
Sure. Okay. Okay, number 1, usually we very quickly plugging every number, we realize this is infinity minus infinity, so can't be handled directly. We want 0 over 0 or infinity over infinity. Second thought, because of the property of Ln, you can certainly do this. Okay, now you realize the inside is 0 over 0. So let's focus on this. Whatever that number is, when we apply L'Hopital's rule, the final number will be Ln of the number. Limit x goes to infinity. No. Okay, without Ln, this is 0 over 0 case. Therefore, we can take the derivative. After that, plugging 1 won't be a problem anymore. Therefore, this is going to be Ln 7 over 5th. Aaron?
4.7, number 4.
4. Find the area of the largest rectangle that can be inscribed in the ellipse. Okay. Now for number 4, you have a ellipse. If you could, try to draw it. Oh, not bad. Okay, so this is an ellipse. And what we want to do is we want to inscribe a rectangle here. And you can see you have many choices. You can have a very skinny rectangle here. And of course, they share the different areas. Now you want to say, okay, which one has the biggest area? That's what you're looking for. Okay, good. With that in mind, maximize the area of the inscribed rectangle. Well, you can see what's changing is the rectangle size. So you can name this one to be X, this one to be Y. That's not to X, Y, that's to A and B. Okay, A for the width and the B for the length. What you notice is number 1, area equals A times B. Now you just need a relationship between A and B, so you can replace one with the other. What you know is they're on the ellipse. Okay, if this is A, what's the coordinate of this point? What's the X value? That's going to be 1/2 A. Do you agree? What's the Y value? That's going to be B over 2. So that's what I find out. If I assign A and B to be like this, then I know A over 2 and B over 2, which will be the point I just highlighted, is on the ellipse. Algebraically, that means if I plug in A over 2 into the ellipse, it should satisfy the equation. 9. Good so far? So here you can solve B from A. It's going to be a Hard, but not impossible. Well, let's times 900 on both sides. This. B equals 900 minus 9a squared divided by 25, then square root. You have positive or negative choices. We just take the positive one. Then the area becomes a times this. As the size of a changes, a goes from as small as 0 as far as 10. Okay, but as a changes, this one changes size. Now we want to find the minimum. So what you should do is you should take f prime a, which is this. Okay, don't be scared by the complicated thing. You can just copy it. Okay, first I have a. Second, I have this. Number 3, I have a negative 18a divided by 25, given by the derivative of the inside. Notice 900 give you nothing because it's 0 when you take the derivative. So what's left is just this. Now set it to be 0. No, it's not too bad. You can times the denominator on both sides. Square root times itself become this. Plus become minus. You have a, you have 2. You have 18a, you have 25. Which give you 9 equals 0. That is 900 minus 9a squared minus 9a squared again, divided by 25 equals 0. This gives you a squared, 18 equals 900. $50. That's your A. If you trust your calculation. Okay. Very quick. Plus minus maximum. So that's the one we're looking for. Then your B is going to be 900 minus 9a squared divided by 25. Oh. What's that? 4, 4, 16, 50, 18, which is 3. Let's go with 2. Then the final area is going to be A times B, which is 5 square root of 2 times 3 square root of 2, which is 30. Sounds good? All right. If you think about it, it's actually not that bad. Remember, if it's a circle, our answer is, okay, it's going to be a square with the square root of 2 here. Okay, that's what happens with a circle. Now for your ellipse, what did you do? You basically stretch the circle to -5 to 5. So you horizontally stretch it by 5. You vertically stretch it by 3. Okay? Then this square, which got stretched with your ellipse, will become a rectangle. Okay? But the ratio should be exactly the same ratio. Horizontally 5, vertically 3. So if you think about it, you're still having the biggest area when you do a square, even after you get everything stretched. That is great. Okay. All right. Nathan?
4.7, number 3.
4.7, number 3. Find the point. Dun, 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 closest to the point. All right. Find the point on y equals this, closest to 13, 0. Okay. If you draw it, it's pretty interesting. Okay, and this is y equals square root of x. This is 13, 0. Somehow you can draw a line here, you draw a line here, you draw a line here. From here, you can see they all share different lengths. So probably you have the one which is closest. Okay. Second, probably it's not as easy as the one which is vertical up, because this one kind of like tends inside. So anything can happen. Now what you can do is closest means shortest distance. So what I would do is I would take D, okay, to be the distance between the point and 13, 0. So this will be the distance. Moreover, I know the point is on y equals square root of x. So if I see an x, by y correspondingly will be square root of x. That will be the setup. Okay, once you have that, you just need to take the derivative and simplify. Like we said before, this is difficult because of the square root. Good news is if you can minimize the distance square, it's the same as minimizing the distance. So let's minimize this instead. Now everything becomes clear. Okay, f prime x. 1 equals 0. This gives you 2x minus 26 plus 1 equals 0. X equals 2 over 25. And then y equals all right. Sounds good. That's pretty amazing. Think about it. Now you can draw any kind of line and just draw any random points and say, hey, what's shortest on the line? Or which point on the line is shortest to this point? You can always do that. Okay. Think about think about the application of this thing, right? For example, you are on some pre-programmed train or something like that. You have to follow this trajectory, but somehow you want to shoot a guy, okay, or shoot a whatever. You want to actually go shoot them when you are closest, so you don't miss that much. Good so far. So this is basically what you're doing in your head. It's just like, when should I just go and pull the trigger? Well, shortest distance. So believe it or not, your mind is always trying to actually do calculus. It's not as accurate as a calculus. It's a different mechanic, but basically you're trying to just find shortest distance. Okay. Another thing, think about the optimization problem we did before. Remember, we were trying to build a thing on the land. It costs less. In the river, it costs more. Right? You can either pick a short distance, but really expensive per mile, or you can just do the cheap miles for a while. It's longer, but you save some money in that way. Sounds good? It's the same thing as, think about it this. If you do a train chase again in Hollywood movie, you have two possibilities, right? The first one is actually you can first get on the train and then run to the bad guy. Or you can ride your Harley Davidson and just directly go to here and catch the guy. Sounds good. You certainly drive faster in Harley Davidson, but the train is also moving. But once you're on the train, you run slower. So do you want the shortest distance, or do you want to take advantage of the fast train? Okay, so it's always a trade-off, and you always have something, right in the middle. Probably just go here and catch the guy. That will be the fastest. So pay attention closely to Hollywood movies. Okay, the good guy never run perpendicularly to the train. And they never drive strictly to the guy. They always go to halfway, catch on the train, and then go there. There is calculus behind it. Okay, same thing with Batman. Okay, good. Other questions? All right. If no question, chapter 4 is over. This is not the last chapter, but roughly the last chapter, chapter 5. Integration. A lot of you have known this before. Basically, we're doing antiderivatives. Okay? Doing the thing is easy. Knowing what you're doing, why you're doing is, I won't say challenging, but is necessary. Think about why do you do integrations? Of course, you were trying to find the area under a curve. We start from there. You were trying to find an area. If I say there's a curve like that, I give you the formula. What's the area under the curve? That's what we're trying to do. Later, of course, we will talk about finding the volume, okay, and everything else. But now let's talk a little bit about what's special about this one, because you know how to find area before. Okay. What's special is this. Before in physics, how do you find the mass of something? It's very easy. It's the density, rho, okay, times the volume, V. So M equals rho V. Make sense so far? For example, how heavy is the water? Well, the density of the water is 1 kilograms per meter square. That's not right. 1,000 kilograms, 1 ton per cube meter. And of course, you have 3 cube meter. That's 3 times this, 3,000 kilograms. Things like that. Good so far? That's nice. That's nice if rho is a constant. That means you have a uniform distributed population. Not population, density. Good so far? Now, what if you want to mix the density? You want to mix, iron and wood together. Okay, for example, you have something like that and consists of 4 different type of materials. This one is light, this one is heavy, this one is right in the middle, and this one is super heavy. Good so far? So you don't have one rho anymore, but no big deal. You just do rho 1 times V1 plus rho 2 times V2 plus rho 3 times V3 plus rho 4 times V4. Okay, you have 4 parts of mass. You kind of decompose them together, and then you just add them. You have smaller volumes, each one with a different density. You add them together, you get the total thing. Still okay? Now you can think about how we push this thing. We can push this one to be 1,000 by 1,000 different grid. You have 1,000 by 1,000 different densities. That's going to be a lot of things to sum. Still okay? But still doable. So what's the limit? If you just keep pushing it, then eventually you have some object. And the density is different anywhere. There's no block. You pick a XY, you have a different density. Your density become a formula of X and Y. You fix a location, I have a density. You move a little bit, my density changed. Make sense so far? Okay. But this time, how do you sum all the different densities together? You have difficulty. Why? Number 1, you have infinitely many blocks. Make sense here? I'm not telling you cut this one into 1,000 pieces. No, cut it into infinite many pieces. Any single place, a point is going to have a different density. So how many do you need to sum together? You have infinite many to sum together. Sounds good? Second, you have another trouble. For each small m, you need rho equals v. But if you're picking a point, this point doesn't have a volume. Make sense so far? What's the mass here? Well, number one, I do have a density here. Number two, I don't have a mass here. Why? Because that thing doesn't have a volume. Sounds good? Can you see? Number one, this one should be doable because nonetheless, it's just like a rock or something like that. That thing has a mass. Number two, the way we compute it should make sense. We just sum each different density with different volumes and sum them all together. But then we have this mathematical difficulty. That is, you're summing infinitely many super small things together. We don't know how to do it. Good so far? That's why we care about how to find the area under the curves. Basically, we care about how to sum infinite many things together. Second thing for you to think a little bit, that is probability. Have you rolled a dice before? Right, you have 6 possible outcomes. 1, 2, 3, 4, 5, 6. Okay. Each one has how big of the chance? 1 over 6, if it's a fair dice. Good so far? Okay. What's the total probability? Just sum them together. And the total probability is always 1 or 100%. That's good, right? Okay. Now think about the following case. Let's say there's a bus. You're waiting for a bus at the bus stop. You know the bus will come between 2 and 3. Good so far? All right. You know this for sure. So definitely it will be no earlier than 2 and no later than 3. The bus definitely come. Okay. What's the chance that the bus will come at 2:30? Let's assume it's equally likely. Any time is equally likely. We call this uniform distribution. Okay, think about the situation. You know the bus is going to come between 2 and 3, and the chance it's going to arrive at 2:30 is the same as the chance it's going to arrive at 2:31. It's the same chance as it's going to arrive at 2:01. Every chance is the same. Still okay? So what's the chance that the bus will arrive at 2:30? Number one, is it 0? No, it's definitely possible, right? Cool. Number two, what is it? Is it 1/10? Do you see the problem here? If you want to answer that question, you need to divide it from 2 to 3 into a lot of pieces. And each piece has 1 over the number of pieces probability. Right? If it's 10 pieces, every piece has 1/10 chance. If it's 100 pieces, every one has a 0.01 chance to be picked. Good so far? But how do you want to divide in this case? Infinite many. It can arrive at 2:30. It can arrive at 2:30.1 seconds. It can arrive at 2:30.1 seconds. Okay? It can be anything. So you have infinitely many little tiny probabilities. Each one is non-zero. And each one is 0 in terms of size. Good so far? And magically, if you sum them together, they equal to 1. You're summing infinitely many little tiny little probability, which each one is almost 0. Sum them together somehow, they have to be 1 because the total probability has to be 1. Do you see the problem here? Okay, that's why we are doing all the area, volume by doing things. Basically, we're trying to chop things into small pieces, but this time, infinite many pieces. And somehow we have a way to sum them together. Of course, thanks to limits. That's what we want to do next. And from here, you can already see it's very useful. Right? What's the probability that that thing is going to arrive at 230? You definitely want to know that. Okay. All right. Now with all the big ideas in our mind, now let's go to the dumb finding the area thing. Okay, the idea is quite simple. Example, find the area under y equals x squared from 0 to 1. How do you do that? That's the area here. Okay. Usually, we start from something simple. I cannot give you the answer. Okay. How about I give you a rough approximation? Okay, because the only thing I know is rectangle. Okay, anything other than rectangle, I can't do it. All right. So what I'm going to do is I'm going to take the whole thing. I'm going to just go from 0 to 1. I divide them into 4 parts. Okay. Then on each one, I'm just going to assume this one is going to be a rectangle. I found this area instead. Doable? Okay, let's try that. Well, we have 4 rectangles, right? We call it rectangle 1 all the way up to rectangle 4. Each rectangle has a width. Let's call it 0.25, 0.5, and 0.75. Width uniformly is going to be 0.25. Each one is going to have a height. Good so far? Okay. According to what I draw it, I pick the height to be the function value of y equals x squared at here, at here, at here, and here for each rectangle. So height 1, x squared, remember? And I pick 0.25. H2, 0.5. H3, 0.75. And H4 is going to be 0.1 square. Finally, the total area. Okay, with 4 rectangle. Should equal the first one times 1/4 plus the second one times 1/4 plus the third one plus the fourth one. Each one is a rectangle. Rectangle is width times height, which give me Sounds good. Okay. This will be my approximation of the area with 4 rectangles. Are you happy? That's my approximation. Is it accurate? No, definitely no. Okay. How do you make it better? Let's do 10 rectangles. That's definitely going to be better, right? What about 100 rectangles? That's going to be even better. Okay. What's the best? 1,000? 1,000,000? Do you see where this is going? You write down what we just did for 4. You do it for n, where n can be 4, can be 40, can be 400, can be 40,000. Still okay? Finally, you let n goes to infinity. Cross your finger and pray that limit exists. Okay, if that limit exists, that's going to be my final answer, and there's no approximation anymore. That's the accurate one. Sounds good? Okay, that's basically the idea behind this. Let's try to see it from Desmos. Of course, I didn't do y equals x squared, but you know what I mean. I was trying to find an area between below this curve. Okay, so basically what we can do is we can do 4. As you can see, well, a little bit more here, a little bit less here, a little bit less here, a little bit more here. Okay, not happy? Increase the number from 4 to 10. Looks better. Okay, from 10 to 33. Now you can see all these kind of small little tiny things. You still have something off, but they become smaller and smaller and smaller. Good so far? Now let's do extreme. Let's just put it to 200. What happened? Number 1, you break Desmos. Number 2, it's really good. Okay. For this one, seems like if you do 2,000, I don't know. Looks nice. Make sense to everybody? Okay, of course, even 2,000 is not enough. We want it to be infinity. Okay, that's what we're trying to do. All right. So before we go ahead and try to do this limit, which is relatively hard, let's write down the idea here. Okay, where is it? Let me share this. Okay. The idea, which is called the Riemann sum. Okay, this is what you have. You want to find the area of fx, actually not of, below fx, from, let's just not say from, on an interval AB. Moreover, we'll assume fx is bigger than 0. Otherwise, we need to find an area above it. So let's, for now, let's just assume it's bigger or equal than 0. Okay, something like this. From A to B. Okay, now what are you going to do? Number 1, you want to divide the interval AB into 4 or maybe 8 or n equal pieces. Something like that. Okay. Then each piece, you have something called delta x, which is b minus a, that's the total length, divided by n, that's how many pieces. That will be the width of the rectangle. Keep in mind. Okay. After that, you can start to draw a rectangle. Number 2, we want to figure out the area of each rectangle. Okay, number 3, we want to sum them together. Sounds good? Now for each rectangle, what do you have? You have something like this. You want to find the area of this and then sum them. Good so far? Okay. What's the area? Well, it's going to be a rectangle. The width is always delta x. Pretty easy. Okay. What's the height? It really depends on how you draw the rectangle. Make sense so far? For the same piece, what I can do is I can draw this one. That's the rectangle. That's one way of doing it. Actually, I shouldn't have done that. I should copy this for several copies. Paste. Paste. Shit. Paste. Okay. Paste. Okay, so we know the height is the key. The width is already fixed. Easy way to do it is just pick it to be this one. This is called left point formula. Okay. The second way, you can actually pick this one. You use the value here to be the height, which is on the ending point. This way is called the right point. Okay. Number 3, you can pick the middle point. Which is give you the midpoint formula. Number 4, actually it really doesn't matter. You can pick this point and do a rectangle, or you can pick this point and do a rectangle. You just pick any point. Just pick one. Good so far? So we're going to say, hey, any point is valid. When will the woodpecker die? November? It's already November. Do they come out during the winter? Hold on. This summer, I found snakes in my basement. I hate animals. Okay, all kinds of animals. The good animal is the one which is cooked. Okay. Either way, pick any point. All right. Make sense here? For now, you'll see a difference. Left point give you a different value than the right point, give you a different value than the midpoint, or any other point you pick. But the beauty is when you let n goes to infinity, it really doesn't matter. Okay? All of them go to the same answer. That's the beauty. Of course, we want to be a little bit careful. How do we want to do this? Okay, so let's be a little bit careful. Basically, the notation. Number 1, this is the IC interval. Let's summarize it. What do you mean? You basically means once you divide everything into here, A and B, we give them names. We call this one x0, we call this one x1, we call this one x2, all the way we call this xn minus 1, and we call this last one xn. So you have a name for each node. Together you can try to see. You have n plus 1 nodes with n interval. Okay. Second, the first interval, the second interval, the third interval, and so on. So the ith interval is going to be xi minus 1, xi. You can take I to be 10. So that's the 10th interval is going to be x9, x10. Okay. Then, if you go back and try to think about this, for the ith interval, the height is basically f xi star, where xi star is a point. In the interval. Then the left point is nothing but when xi star equals the left one. The right point is nothing but when xi star equals the right point. Okay, and the third one is nothing but xi star equals xi minus 1 plus xi divided by 2. Sounds good? And you have the freedom to choose which xi star you want. But either way, once you choose the point, the height is just going to be plug this number into the function. That's how tall this is. Sounds good? Finally, number 3. Total area. We give it a name. We call it Riemann sum. With n squared, so we gave it r. We call it n. It's going to be the sum from I from 1 to n. Here you want to put each rectangle. You have n of them. Okay. Here is the height. Here is the width. Okay. With delta x given by the size. Sounds good? Finally, number 4. The area, the real area, equals limit n goes to infinity Rn. Provided that the limit exists. Okay, take a look. And I accidentally locked my wife outside my house. I'm gonna go down and unlock the door. Okay, you guys read this just before she freaks out. Okay, she's not too mad, so I still got lunch. Nice. Does everything make sense here? Okay, let's repeat it really quickly, and you try to repeat it in your head too. Okay, we have an interval. We divide it into 4 parts, 10 parts, whatever, n parts. Okay. For each n, it's going to be a rectangle. Each rectangle has an area, which has a width and a height. The width is going to be the original length divided by n. Okay, the height is going to be the function value. I just need to pick which function, which point. Any point in that interval works. If I pick the left, I got a left point formula. If I pick the right, I got a right point formula. If I pick the one in the middle, I got a midpoint formula. Okay? They give me different answers. Take the sum, I got the Riemann sum with n squared. And finally, I let n goes to infinity. That means I take infinitely many squares, rectangles. From there, when you take the limit, it doesn't really matter if you pick the left, right, or midpoint, or any other sample points. They all goes to the same limit. Okay, so no matter how you do it, even though when you do the approximation, the answer may look different. But once you take the exact value by taking the limit, they all look different. So it doesn't really matter. Sounds good? For simplicity, for writing things down, we pick a lot of things. Number one, we pick every interval to be equal. In real life, it doesn't have to. You can pick someone to be wider, someone to be narrower. Eventually, when you take the limit, it doesn't matter because you have infinite many. Okay? Now we have the same way to pick the sample points on each interval, but you don't have to. On the first rectangle, you can pick the left. On the second rectangle, you can pick the midpoint. On the third one, you can pick the right point. Sounds good? But all you did is just basically creating yourself for trouble because, again, all the answer goes to the same thing. So it really doesn't matter which one you pick. How about we just pick something uniform so it's easier to compute? That's the idea of Riemann sum. Let's do some example on this. Later we will talk about will the limit always exist? That means will we be able to always find the area under the curve? Okay, and of course the answer is no. Sometimes you have some really bad things, you cannot find the area. Actually, we have less than 10 minutes left. Let's save the examples for next time.